Where is everybody? I guess they're all studying for the midterm. Or else they tried studying for the midterm and gave up, one or the other. Okay, so we're having a midterm this evening, 2050 VLSB, be there or be square. And we're going to talk some more about logo for two reasons. One is that you're doing a programming project implementing it. And the other is to illustrate some of the questions of programming language design. So we're going to say, how come scheme is this way and logo is that way? And most of the answers about those differences come down to the fact that scheme is a language for adults and logo is a language for kids, which is partly saying scheme is a language for professionals, like you guys, and logo is a language for amateurs, tinkerers. So we'll see how that affects the different decisions that were made. Although sometimes there isn't a good reason. It's just, history of what was going on at the time. Okay. So I mentioned at the end of last time that in logo, there are certain procedures that return values, and they're called operations. There are other procedures that don't return values. You call them for some action that they're doing, like printing something or changing the value of something. And they don't return a value. So let me just run down the big points. Scheme has a single namespace. That is, any symbol is only ever the name of one thing. And that has to do with the fact that everything in scheme is first class. So anything, including a procedure in particular, could be the value of a variable. Logo, like earlier Lisp dialects, and also like Common Lisp, by the way, which is the sort of industrial strength Lisp that people use out in the real world when they use Lisp at all today, has two namespaces, one for procedures and one for everything else. Why is that important? Well, often, like every day, when we're writing scheme code, we want to have a formal parameter that's list or word or sentence, right? And we don't. We call it LST or SENT or WD because in scheme, if we called it list or sentence or word, that would make the constructor procedure for that data type unusable inside the procedure that had that formal parameter. In logo, that's not the case. So I can have, if you look down here, jumping ahead a bit, I can have my Pig Latin procedure has a formal parameter, word, and it also is using the procedure word, which is the constructor for words. Okay? So two namespaces, one for procedures, one for everything else. Actually, in logo, in traditional logo anyway, there's a third namespace. The same symbol can also be the name of something called a property list, which we aren't going to worry about here. Scheme is lexically scoped, logo is dynamically scoped. I'll talk more later about the implications of those choices. Scheme has first-class procedures, logo doesn't. So that's a huge difference, right? First-class procedures is at the heart of everything we've been doing all semester. But it turns out that if you have have a dynamically scoped language, then you can just quote an expression, and that expression is just as good as a procedure to compute that expression. What do I mean by that? So let's think about dynamic and lexical scope a minute. Lexical scope means that when you make a procedure with lambda, there are two parts to the procedure. The left bubble, which has the information contained in the lambda expression itself. namely the parameters and the body. And then there's the right bubble that says, where was this procedure defined so that we know what environment to extend when we call this procedure, right? That's lexical scope. We talked about environment diagrams a lot. I hope you know that. You're going to need to know tonight. In a dynamically scoped language, when you call a procedure, you make a frame binding the formals to the actual argument values, and then you extend the current environment. So there's no right bubble in a procedure. Well, if there's no right bubble, then a procedure really boils down to just the text of the procedure. So in Scheme, a lambda, the procedure created by lambda carries with it values for certain variables, right? The variables that are inherited from outer scopes, like if you have a let outside a lambda. But none of that is true in Logo. If we did have first-class procedures, if we had lambda, the procedure that was created by the lambda would just be the text of the procedure, the way it was in the Scheme 1 interpreter. Scheme 1 wasn't dynamically scoped, but it used the substitution model, and so what was in the procedure was essentially a modified version of the text of the lambda, with substitution having been done already before we even saw the lambda. And so we're going to see in a bit that in Logo, we can just use expressions the way we use first-class procedures in Scheme. So we can make higher-order functions based on just expressions. And finally, as we saw last time, Scheme, you always put parentheses around every procedure call. Parentheses are never optional. They always mean something. And what they usually mean is we're calling this procedure with those arguments. And that means in particular that you can tell the difference between a procedure name that we're calling and a procedure name that's providing the argument to some other procedure like map. And the way you can tell is if the name has a left parenthesis right in front of it, then it's being called, and if not, not. In Logo, we don't fully parenthesize things. And so in order to keep straight the difference between arguments and procedure calls, we have to know the arity, which is the fancy term for how many arguments does this take, of every procedure. So every procedure has a default arity. Some procedures can have variable arity if you use parentheses around the calls, as in Scheme. Okay, so this is, in Scheme, everything has very, very simple uniform rules. In Logo, there are a lot of compromises. And they're compromises because of what people expect. Right? So people expect to be able to do infix arithmetic. People don't like lots of parentheses. If you can remember back a few months when you started this course and you saw Lisp code and you said, ugh, right, all these parentheses. So in Logo, we don't give people a chance to say that because they don't see all those parentheses. But instead, the Logo interpreter has to know the arity of every procedure. Okay, so let me show you a couple of simple examples. Let's print second of am I loving? My. So how does second work? Well, it has a formal parameter. So 2 is like define plus lambda. Right, so it says create a procedure. So toSecond, the reason it's 2 is think about telling a human being how to do something. So you would say, to differentiate a polynomial, blah, 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 right? To get from here to Soda Hall, go out the door, turn right, okay? So that's the sense of 2 that we're using. I'm telling you how to do something. So toSecond, and then comes formal parameters, and they have colons in front of them. And we'll talk about the colon in a bit. For right now, it's just in the title line here, it's just a piece of syntax to remind you that this is a formal parameter and not the name of the function. So to second dots thing, and yeah, that's how we pronounce colon. We logo, I'd say dots. So you'll hear me say that a lot. So this part you'll recognize, first of but first of dots thing. In Scheme, it would be open paren first, open paren, but first, thing, close paren, close paren. But this means the same as that, because the logo interpreter knows that first and but first each take one input. And if you have just a symbol by itself, that means you're calling a procedure. It's a procedure name, and you're invoking it. If you have a colon in front of something, it means we're looking for the value of a variable. What's new to you is this output. Output is a command. Everybody gets confused about this. Output is a command that you can only use inside a procedure definition, and it turns the procedure that it's in to an operation. So output itself is a command, but second is an operation because it says output in it. And output takes one input, one argument, and it says the procedure that I'm in should return this value. Okay? So if I just said first of but first of dots thing, it would be like saying first of but first of help. I would get an error message. You don't say what to do with. Well, the same thing is true inside a procedure body. If you want your procedure to output that, you have to say so. And one of the reasons for that is instead of saying output here, I could have said print, in which case my procedure would be a command. It would print something and not return a value. So my twice procedure does that. Twice, prints its input twice. Okay, notice, by the way, that there aren't any brackets around the printed value. We'll talk about that in a second. Okay? So twice does not return a value. I couldn't say print twice, nowhere man. If I did that, let's try that. I get the error. Twice didn't output to print. Oops. Okay, so I'm doing print. That means whatever comes next should provide the input to print. What comes next is a procedure call. So logo runs the procedure. It prints nowhere man twice. And then twice is supposed to output a value that print can print, but it doesn't. Okay, so I get the message, twice didn't output to print. By the way, remember the first time you saw a scheme error message and you could barely see what the actual error was because there was this whole backtrace underneath it that you didn't understand, and it was a little intimidating? And furthermore, if you did see the error message, it said something like unbound variable, and you had no idea what unbound meant. One of the things that distinguishes Logo as a language is that we put huge amounts of effort into the error messages. The error messages are supposed to be non-intimidating. And in general, we try to phrase things so that it doesn't sound like you're a bad kid having done this. So it doesn't say you gave a command where an operation was needed. It's twice's fault, right? Twice was supposed to output to print and it didn't. So we really think about things like that in Logo error messages. In fact, I'll tell you a story. Foo. I don't know how to foo. So two things about that message. One is I'd like you to notice this very subtle extra space in here. That's supposed to be a reminder of how to fix this problem by saying to foo, do blah, 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 right? Secondly, it's I don't know how, right? It's not your fault. I don't know. Although some people, that's a little controversial. People write academic papers about this subject. Some people worry about anthropomorphizing the computer. So gives kids the expectation that the computer is smarter than it is. So some people prefer you didn't say how to foo. So that's a question of a little bit of controversy among computer language writers. But the real story is the original version of Logo had a different error message in this situation. And the message was, foo has no meaning. And this lasted until my friend Paul Goldenberg, who was one of the early Logo researchers and the world's best teacher, and a great guy, was working with 5th graders, I think, or 7th graders, somewhere in that range. And one day, this little girl came up to him in tears because she had typed into Logo, love. And the computer said, love has no meaning. The next day, there was this error message. Okay? Yeah, I don't know how to love. Well, it's better than love has no meaning, right? And computers don't. Computers don't know how to love you. They know how to hate you. That's a different story. Okay. Moving on. Oops. I said, oh, whoops. That's the problem. So here's Piggle. So I say print Piggle quote logo lay. Right, Piggle quote scheme, all that. How does it work? Well, if vowel P first word, if the first letter of word is a vowel, and then there's these square brackets. Inside the square brackets, it says output word, dots word, quote AY. So here, word is the constructor procedure with 2 inputs. The first input is our actual argument, whatever corresponds to the formal parameter name word, and then quoted AY. So notice that you do the quoting with the double quote character, the one that you used to think of as quote before you came here. But there's only one of it. It doesn't come in pairs. So it acts like the scheme single quote, but use the double quote character for quoting. But the interesting part is these square brackets. Square brackets in Logo mean the same as quote parenthesis in scheme. Namely, I'm both delimiting and quoting a list. You can have brackets inside brackets, and those are just like parentheses in scheme. But the outermost one implies a quotation mark. If you don't want to quote something, then you don't need any delimiter at all. You just do it, right? So I guess I should write this on the board. About a dozen special forms in scheme. There's only one special form in Logo, and that's 2 for defining procedures. Everything else is an ordinary procedure that evaluates its arguments. Now, you will remember back in week 1 of the course, you proved that if had to be a special form, right? That doesn't seem to be true in Logo. Why not? Well, because quoting the thing that you want to do is good enough. If we get around to saying eval this expression, which is essentially what if does, it will inherit the argument of the caller of if, right? So if could be a user-defined procedure. In fact, in a bit, I'll show you how to write if without having any conditionals in the language at all. It's very cute, but we're not ready for that yet. So this is what I mean by saying that an expression in Logo is like having a procedure in Scheme. So if we wanted to do this, equivalent to this in Scheme, we would write an if that said if, parenthesis, vowel p first of word, close parenthesis, open paren, lambda, left paren, right paren, output, blah, 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 right? We would have to make a procedure to be the second input to if. If in Logo takes two inputs, by the way, thing to test, what to do if it's true. If you want the three input kind, like the Scheme one, that's called if-else, one word. If-else, test, what to do if it's true, what to do if it's false. Okay? So another thing to note about this is if we do evaluate this output expression, output ends the procedure. So this line after that doesn't have to be part of an else clause because the then clause here ends the procedure. As soon as you execute an output, the procedure is done. If that's not the case, if first of word is a consonant, then we say output, recursive call to Piggle, word, but first of dots word, first of dots word, which is the same way we did it in Scheme. Okay? Here's vowel P, letter, output, member P, dots letter, quote, A-E-I-O-U. That's how you see if something is a vowel. By the way, what is this member P, vowel P about? P stands for predicate. There have been huge, huge screaming arguments among Logo designers about how to represent predicates. And there are basically three contenders. One is question mark, as in Scheme. One is vowel P, as in the most traditional Logos, and the most traditional Lisps. Lisp always originally used P, which has survived in the language of hackers. If you're hungry and you want somebody to come eat with you, you go up to them and say, food P? And they know what you mean, even if they program in a Lisp that has question marks. So P for predicate, or question mark for question, or the third contender was some British versions of Logo used Q. And Q is a kind of compromise candidate, because one of the problems with question mark, as you may have observed, if you want to say a Scheme program to someone, there's a procedure called list that's the constructor for lists, and there's another procedure called list, which is the predicate for is this thing a list, and it's, so you end up saying list question mark, you know. List P is a lot easier. But Q is pronounceable, so you can say list Q, but it's an uncommon letter. You're not likely to have a name that ends in Q by accident. So that's the advantage of Q. It's actually not a bad choice, but nobody uses it outside of Britain. I was always a P fan, mainly because of this list problem. But also, I claim every procedure that returns a value is answering a question. So when you say plus 2, 3 in Scheme, or sum 2, 3 in Logo, you're asking a question. What's the sum of 2 and 3? How much is 2 plus 3? Question mark. Right? In English, you'd have a question mark for that, the same as you do for predicates, which are yes or no questions. So I think that to make the idea of predicate mean the same thing as the idea of question is confusing. And that's why I like P. It's more specialized. People who don't like P point out that there are primitive logo procedures whose name end in P that aren't predicates, like stop is one. And so people who would, question mark fans would make fun of us P fans by talking about the primitive stow P. A mispronunciation of stop. So in the design of Apple logo, in which I participated in about 1 trillion design meetings, at which there was huge extreme arguments about this, I ended up winning. We used P. The argument that convinced people, in the end, was one that I made as a joke. I said, anyway, look, the scheme prompt is a question mark. So if you say, if you say word question mark, it looks as if you're delimiting something like, the upside down question mark in Spanish at the beginning, And they said, oh yeah, huh? Oops, oh well. Hey. Yeah. And so that's how I won the argument. Okay, let's move along here. Essentially no special forms except for two. In particular, if isn't a special form. And so almost all the time, you see square brackets here. That, by the way, was also controversial. In the original Lisp, if was a special form. And the notation was if test, then what to do if it's true. And then you could say else if you wanted to and have another thing. Just like, all those other programming languages. And I hated special forms, so I made them do it this way. And the problem with doing it this way is people always ask, how come this is in square brackets, but this isn't in square brackets? And because you understand about evaluation, right, and that we want if to evaluate this other thing only under certain conditions and all of that, you know why there are brackets on the second one but not the first one. But it's a little hard to explain that to a kid. And so that was another thing we would argue about. It's also hard to explain 1 million special case rules to a kid. So there are advantages to uniformity also. Okay. Oops. So here's just the standard but first your way down a sentence kind of recursion. I say print pig Latin another girl. Not a great example. Oh well. All right. Print pig Latin. There, lots of consonants. That's better. So how does this work? It has a base case. If the sentence is empty, output the empty sentence. Otherwise, output fput. That's cons. It stands for first put. So put this at the beginning of that. There's also, in Logo, lput, which you would have liked when you were trying to reverse a list the first time. So fput, call piggle on the first word of the sentence, and call pig Latin on the but first of the sentence. So it's just like cons. I could have said here, of course, instead of fput, sentence, and it would have done the same thing, right? It would have had the same result. And that's what I would do if I were writing this for a kid. But here I'm writing it to teach you about fput. Okay. Print factorial 10. and factorial 6, whatever. Okay, so that's the same factorial program you know and love, except that it's using infix arithmetic here. Infix arithmetic has a problem about figuring out precedence. So you have to think carefully about, for example, why doesn't this take the factorial of n and subtract 1 from it? Or n times the factorial of n and subtract 1 from it. And the answer is that infix operators have higher precedence than prefix operators. Sometimes that's what you want and sometimes it isn't. But then you can change it with parentheses. But it's the problem with infix is that you have to think about order of operations. Oops. Oh, word. There. Hello, 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 hello. So this doesn't actually work by constructing this long word. It works by calling type. Type is like display. Type is to scheme display as print is to scheme print. Namely, it prints the stuff and doesn't start a new line. And then here, after we've done that num times, we print the empty sentence, and that gets us onto the next line. Okay? Oh, and here's good old Stopy. If number is equal to 0, then stop. And then we don't do all the rest of this stuff. Okay? I could instead have said if number greater than 0, left bracket, and then all the rest of this thing, right bracket. That would work. That would have worked too. But this is more traditional logo style, that if base case is reached, stop. Otherwise, do these things. And finally, a recursive call. This is, of course, a tail call. The Berkeley logo interpreter does recognize tail calls and do tail call elimination, although it's a real pain in the butt. Because of the difference between commands and operations, that confuses things a lot in the interpreter. Okay. Check this out. Oh, the third kind of print is show. Show is just like print, except if the thing you're printing is a list, it puts square brackets around it. The reason print doesn't is that the main use of lists in Logo is for sentences, for like English sentences. You're writing a program that carries on a conversation with the user. You don't want to see brackets around everything the computer says. You want it to look like, you know, having a conversation. So when you do want the brackets, because you're really trying to delimit something or emphasize that it's a list, you can use show. So I'm going to say show map function over list of numbers. Okay, so this $ times $, that's the square function. This is not the way you would do it in Scheme. In Scheme, you would say lambda of x times xx. So this is kind of an automatic formal parameter. And the reason for that is so remember those Piagetian stages that Alan Kay talked about, the doing stage and the sort of visual stage and then the symbolic stage? So visual stage kids, which means up through age 12-ish, can't do algebra. You can tell them about variables and they'll sort of get it. But if you say, x plus 4 equals 7, young kids will have trouble knowing what you're asking them. Whereas, if you say box plus 4 equals 7, then every third grader can do this. Because it's a visual language. If you have a box like this, it's clear that something goes in the box. Right? Whereas with X, that's not obvious. So visual dominant kids need a visual cue about the variableness of something. So because of that, this is my invention, what you're looking at right now, actually. It's one of the things I'm proud of about Logo. I wanted to have box in the language, but unfortunately box is not an ASCII character. So the character I picked is question mark. So if you see, you're a kid, and you see something that says question mark times question mark, okay? I figure that's about as close as I can get in ASCII text to something that's going to make it visually obvious that you're supposed to put something in here. So we're asking the question, what times what, right? Okay? So that's where this notation comes from. But the cool part is how we can write this program and the fact that it relies on dynamic scope. So let me move up. There. Okay. The reason I'm using $ here rather than question mark is that the apply function is actually primitive in Berkeley Logo, so question mark is kind of taken. And I wanted to show you how it's implementable. So map function over a list. If the list is empty, output the empty list, just like scheme. Output cons call the function with first of dots list as its argument. So that's what's going to be the first element of the result. And the thing we're consing that onto is map the function over the but first of the list. Okay? So that's map. Everybody understand that if call works the way it should, then map will work the way it should, right? Now in scheme, I could have just said fun of first of list. But fun isn't exactly a procedure. We don't have first-class procedures. So I have to invent this thing call, which is a little bit like apply, except that there's, instead of a list of arguments, we just give it the argument. The real one that is built into Logo actually is very much like apply. It does take a list of arguments. But I wanted to make it simple in this example that I'm showing you. So to call function argument value, if function is a word, never mind that. Function isn't a word. It was that list, question mark times question. It was $ times $. So I say output run dots fun. Run is a Logo primitive. It's eval. Now, why doesn't it take an environment? Because it evals in the current environment. Okay, implicitly, it has the current environment as the evaluation one. So how can we evaluate $ times $? Well, because I wrote a procedure, $. What does $sign do? It outputs dots arg value. Is there a global variable dots arg value? No. If I say print dots arg value, has no value. Means unbound. Is arg value local to the $ procedure? No. Is this $ procedure defined inside of something, lexically inside, that has an arg value? No. But there is arg value in the current environment. because the current environment of $ extends the environment from the call to call, okay? Because that's dynamic scope. So this $ procedure can refer to an argument to call. So call and $ work together to provide this sort of box-like capability for indicating argument slots without explicit use of a formal parameter. And I think that's the kid-friendly way to do it. Those of you who took CS10 will recall seeing blocks with empty input slots used as inputs to higher order functions. It's the same idea. Except in BYOB, it really does look like a box. It's just like that. But, you know, Logo, we're limited to text. OK. I'm actually more or less on schedule for a change. Let's see. What haven't I done here? Nothing. I'm at the end. OK, great. So you guys are so lucky because you're getting this course from me. Everybody else, every other computer science person on Earth will tell you dynamic scope is just a mistake. Lexical scope is the right thing. And the reason they all say that is that they're envisioning industrial computer programming. Right? We have a lot of people working on a computer program, and it has to work every time. It's got to be bug-free, and it has to be fast, because it's going to be used over and over and over again. Right? In education, the program isn't going to be used over and over and over again. As soon as it works, you go on to the next exercise. Right? It doesn't matter that much if it's fast, as long as it's not excruciatingly slow. And so the values are different. And so if you're writing a language for kids, I claim, you want it dynamically scoped. Parenthesis, BYOB isn't. It's lexically scoped. And later on, people who are BYOB fans, we can talk about why that is. But I don't want to confuse things right now. Smalltalk is dynamically scoped. Alan Kay's language for kids. OK. Lexical scope is good because, as you know, if you have lexical scope and you also have lambda, then you get free object-oriented programming, right? Because you can have local state variables by putting a lambda inside a let, right? Or in other words, a lambda inside a lambda, basically. And lexical scope plus lambda gives you that. Now, most lexically scoped languages don't have lambda, although that's starting to change. I think for people my age, this is really very amusing. It's one of those amusing things. 50 years ago, 60 years ago, when Lisp was invented, everybody immediately started making fun of it. 50 years later, everybody's still making fun of Lisp. But now, their favorite language also has lambda. Right? So it's like we're losing the battle of what the language should be called, but we're winning the battle of how it should work. Anyway, so lexical scope allows local state variables. Dynamic scope allows first-class expressions. OK, so the example I just showed you with map. Depends on dynamic scope. Because it means that an expression is as good as a procedure would be given dynamic scope. Whereas in scheme, quote times XX is a very different thing from lambda of x times XX. But in Logo, they're not so different. OK, lexical scope prevents name capture bugs. What does that mean? Suppose I say, kind of a silly example, define, no, not scheme, Logo. Make, quote, pi. Make is a combination of define and set bang. It just set the variable to this value. If it didn't exist, make a global one. It's not a special form, so I have to quote the variable name. 3.141592654. OK, now I say, to pumpkin.py print, I don't know, area 5. 2, area dots radius output, abbreviation for output, dots pi times dots radius times dots radius end. Okay? So now if I say print area 5, that's 25 times pi, basically. 25 times 3 would be 75. It's a little more than that. Okay? Now if I say, now if I say pumpkin 4, the area of a circle of radius 5 has become 100. Right? Not out here. Print area 5. This still works. But because pumpkin happens to have pi as a formal parameter, this procedure area, which thinks it's using the global variable pi, is actually using this local pi. That's called name capture. Pumpkin is capturing the name pi that area expected to mean something else. Okay, so that's a source of bugs in dynamically scoped languages. And it's true it is, although sometimes it's a behavior that you want. Remember the time that the legislature of wherever that was almost did declare pi equal to 4? You know that story? Some idiot state legislator decided that arithmetic was too complicated with pi having this screwy value. And it would be so much easier to do engineering computations if pi were 4. So he introduced a bill declaring pi to be 4. And luckily, some statistician from the university of whatever state it was happened to be visiting the legislature that day about a completely different issue and, you know, hit the roof and didn't let them pass the law. Anyway, so name capture bugs. On the other hand, it lets you have what I'm calling semi-global variables. What I mean by that is I'm a kid, I want to draw a picture, and the picture has a house and, you know, a door and a window and whatever, and there's a path leading up to the house, and there's a nice fractal tree next to the driveway, and there's a car on the street, and all of that stuff, okay? And now I'd like to be able to do this in different sizes. So I'm going to have a procedure to picture dots size, and then it's going to say house, road, tree, car, end. Okay? Typical kid procedure. In house, I'm going to say to house, and then I can say, you know, forward dot size, etc. Move that many steps. If I wanted to do this in scheme, all of these procedures would have to take size as an argument, right? In Logo, I don't have to do that. That's what I mean by a semi-global variable, and it's just sometimes very convenient. And kids, you know, understand it perfectly well. Finally, good thing it's finally, because we have 1 minute left. A lexically scoped language makes for faster compiled code because the compiler knows which variable, which binding is meant by any variable name reference without running the program. Because The variable name refers to a variable of this procedure, if there is one like that. Otherwise, the enclosing procedure in the definition, otherwise the enclosing procedure of that out to the front. So the compiled program doesn't have any variable names in it at all. It says something like, look at the third slot in the fourth frame back from this one. And that's just a few machine instructions to jump around to there. A dynamically scoped language, the same variable reference can mean two different variables, as we saw about this variable reference, depending on the context in which the procedure is called. So you have to look up the names at runtime, and that slows things down. On the other hand, if something goes wrong, and your program has an error, I don't have time to actually show you this, but you can have the program stop at the point of the error, give you a logo prompt, but in the environment where the error happened. And because of dynamic scope, you can see the variables of the procedure where the error was found, the variables of the procedure that called it, the variables of the procedure that called that, because the actual mistake in your program, I'm sure you've had this happen, the bug in your program might be in a different procedure from the one that actually had some primitive blow up, right? Maybe your procedure A called procedure B with an invalid value, and B called C, and C called some primitive that blew up, right? So in order to find the bug, you have to look at the variables of procedure A, and with dynamic scope, you can. It's just there. Lexically scoped languages have to give you this complicated interactive development environment thing where you use mechanisms outside of the language to look around the environment. Okay, see you Friday. Oh, I'll see you tonight, sorry, then Friday.